Our next speaker is Herin. He's the Director of Standardization within the CTO office at ATEM. He helps their research and innovation team develop future technologies for video processing and delivery, and drive partnership projects and standardization advances. He's also a co-chair of the ATSC planning team number 9, studying sustainability of media and data distribution. He holds a master's degree in mechanical engineering. Oh boy, I'm going to break my tongue now. From the Université de Technologie de Compiègne. Okay, what he said. And he plays handball for the New York City team handball club. In his presentation, he will examine practical deployment aspects of SGS for both file and live delivery, and focused on optimizing delivery for mixed environments of legacy and FGS-enabled clients. Please welcome Robin.
Thank you. It's working. Perfect. Good morning, everyone. Oh, a little loud, I think. So welcome to this presentation. I wanted to present to you some of the work we have been doing within the CTO office focused on film grain synthesis and the actual implementation within today's workflow. One of the major questions we asked ourselves as part of the study was, how would we go today at implementing FGS within an existing media workflow within the current ecosystem? How do we assess the gap between where we are today and where we need to go in order to not only just be able to provide transmission of FGS and content with actual grain properly, but still support some of the legacy devices that we still have on the field today? So as part of this questioning, we asked ourselves, well, first, let's look at actual FGS adoption itself. So if you look at film grain synthesis, most of the technology is FGS within the AV1 codec, and then you also have the specification around AFGS1 itself. Other FGS technologies are a little bit behind at this point in terms of adoption, so we're focusing on these two for this study itself. FGS is obviously supported within any AV1 capable device. It's baked into the codec itself. But that does not necessarily mean, on the other side, that AFGS1 is supported for HASC and BBC. It's more of a methodology to use for other codecs, but it's still currently being in the process. If you look at the deployment base, as for AV1 devices on the field today, there's no publicly available data, but we know that it should be around a third of the devices and around this more or less are AV1 capable, with a continuing rollouts that will allow us to have around 50% of devices on the field today in 4 years, that will support AV1. On the other side, AFGS1, the situation is a bit more different, and it depends on where the film grain synthesis was actually added. If it's baked into the post-processing, then at least we can just do the film grain synthesis as a post-processing. If it's actually within a decoder, then that means you need to have a decoder per type of codec, which is a little different. An example of a scenario for this is the latest announcement on some of the mobile devices, for example, Apple, who have implemented a dedicated AV1 codec with FGS, which means we may not be able to use the same film grain synthesis for another codec in the future. So overall, in the next 4 years, you can see there's a main addressable FGS device population that is going to be AV1 capable, and as such, FGS capable. Film grain synthesis can only be introduced if you consider not just the AV1 capable population of devices, but also the larger population of any devices out there that are not going to be supporting FGS itself. So again, thinking about how we handle FGS capability, there are 3, I would say, either caveats the question you need to ask yourself, or 3 realizations. One, there is today no mechanism to actually signal whether an end device, an endpoint you're reaching out to, actually supports FGS itself. That obviously isn't true if you have you're within an application environment, or within it if you're using AV1 as well. There is no signaling either within OTT streams to indicate the presence of film grain synthesis at a higher level. And on the other side, you have the delivery infrastructure that can only measure how many de facto clients are fetching the content, but may not necessarily be able to actually know what's the amount of them that are actually fetching content with FGS or an AFGS1 stream. Obviously, if it's using AV1, any device consuming AV1 is de facto capable of AGS, but again, that still limits the amount of analytics that you can get from this. How do we solve these three problems? Well, potential resolution could be done with an actual whitelisting of devices with the help of user agent strings that could help some better predictability of the endpoints. We could also use a custom key in SAMCD that could be used to communicate between the CDN and the clients. Set key, as of today, has not been defined, but it could be created as a way to signal the capability that FGS is actually supported by the clients. So overall, on AV1 coded streams, FGS can actually be introduced without restrictions. AV1, as a result, could be introduced as a way to be able to handle film grain synthesis. For the codecs, there is currently no way to target FGS-only enabled devices with film grain synthesis streams. So that means we're kind of in this situation where we're trying to we have a one-size-fits-all problem where we're trying to address a whole market with very limited options, while still, again, respecting, and I think that points out also to previous presentation, respect the artistic intent while still reaching out to legacy devices. So as part of film grain synthesis, let's go back to the basics, which is addressing the type of content itself. Well, if you look at what is being done on linear programming today, obviously FGS performs differently depending on the type of content itself. Grain is going to be FGS is going to be a lot more performant on grainy contents. Grainy content mostly present on drama or documentary. It's obviously not going to be a lot less likely to be useful for any news or weather reports, talking head, even ads as well. As part of some of those gains you can get with FGS, we can see on drama and documentary up to from 30 all the way up to 90% gains using FGS. As part of the encoding, whereas obviously on any ad or any talk show, you basically will see very little gains at all. Obviously, what that means is that there's going to be huge differences in variation between on the bit rate, depending on the type of contents. Overall, the point of this is the consideration of encoding simulcast with FGS. If we're trying to actually look at both addressing the devices that can support FGS and legacy devices at the same time, we need to understand to consider the variability of the content itself and the programming. So now that we actually see a little bit of a state of the art and we have looked at we've assessed at least what is some of the issue, how do we preserve grain in an economically viable way, in a way that can be implemented in the near future? So one possibility, one method is to actually look at grain preservation mode. It's something that's found in encoders like X264, X265. Main principle is to preserve the energy density while reducing all the compression techniques. That includes post-processing and pre-filtering, post-processing and pre-processing filtering, quantization, motion estimation. Using all of these compression techniques that could reduce the grain at the price of a slightly higher bit rates. The benefits is it allows you to preserve better grain without pushing the overall quality to a point that you're basically allocating too many bits to the stream. It results in a bit rate that shows something that's intermediate between a full FGS implementation and a grain version that would be conventionally encoded without any specific parameters. The main use case that you could address with this would be to preserve grain on a low population of end devices that support FGS. It avoids any simulcast, but it at least addresses that use case. At the same time, we have also a possibility, which is doing simulcast between FGS and grain preservation mode. We can also do that with shared resources, so that at the point where a program, a specific channel actually has a program that has some film grain, you can actually trigger a simulcast that will automatically encode using film grain synthesis, and then go back to the regular linear encoding without that option if there's no film grain. So in this case, you basically have two specific instances for the same program: your regular encoding for your regular program with your regular channel, and then a second encoding that would benefit from the film grain synthesis with again the actual FGS metadata that comes with it. The additional FGS encoding could be using AV1, and then you can actually spread the extra encoder resource in a way that can be mutualized across multiple channels. The main benefits is that in this way, since you're doing simulcasts, you're making sure that there's no compromise on legacy devices. You're basically addressing the entire market. You can mitigate the costs of accounting for some of the share of content with grain to preserve, because you can basically allocate shared resources dynamically. And finally, the simulcast benefits of the HGS, but also you have still some potential AV1 efficiency gain just due to the codec itself. So again, this would be a good use case for if you have additional encoding shared costs, but that are lower than the total distribution costs for the FGS capable devices. Finally, a third potential way of addressing this would be to do grain attenuation. So basically taking in your contents and partially preserving the grain. So that means you remove some of it that you can actually then synthesize with FGS while still keeping some of the grain within the content itself. In this way, you avoid the extra encoding, so you're basically avoiding an extra pass, which is obviously some additional efficiency. And then you can have a more progressive adjustments of the scaling itself, depending on how many FGS capable devices you have out there. If you have a low population of FGS capable devices, you may have to preserve more grain. If you have higher population of devices out there that support FGS, then you can actually preserve less grain and actually scale more onto the FGS itself. In terms of mindset, it's kind of similar to what was done for HDR dynamic adjustments for HDR10 devices and HLG10, more or less, backward compatibility with devices. So in that scenario, the main use case would be addressing, a low to high population of FGS capable devices, but especially a population that is transitioning between the two. And on top of this, it also avoids any simulcast in AV1. So now if you look at a detailed technical transcription of how we would potentially implement this last method. Obviously, this is a typical FGS chain. You basically have your input contents. Through grain processing, you can actually get the grain parameters, then can be transmitted to the proper encoder. The video itself doesn't have the grain anymore. We encode the stream. At the decoder level, the decoder is capable of resynthesizing the grain itself on top of the grain video entirely. Then we look at grain attenuation and how would we implement it. So we would split the grain into two additional parts. So you have a grain scaling. Basically, you can more or less say how much of the grain you would like to preserve or not within the content, it's within the raw video, and then how much of the grain you would actually pass over to FGS. In that scenario, that means you have one part of the grain that is basically reintroduced in the video, and the other side that is basically synthesized and can be reconstructed by any device that supports FGS at the decoding level. So AFGS1 film grain is pretty much already including this parameter. So there's an actual scaling parameter, there's the grain strength that is existing within the technology. From a given set of grain parameters, you can actually easily modify the scaling itself. And as Hojat was actually showing earlier, there is a randomized function that exists within FGS that is baked in, which means the randomized number is right there, and the superposition actually does not create any artifacts or anything. It's immediate. Now, why does it make sense actually to go this route potentially? Well, we want to actually look at proper evaluations, some objective at least metrics. So we decided to look at bitrate and bandwidth efficiency if we try to implement such a method. Well, if you think about the following types of contents, I think those are contents that we actually are open for anybody to do some research with. The indicated bit rate below, it's the bit rate at which the encoder struggles to preserve the grain. The encoder itself is our RTM encoder, but the same experiment can be conducted with X265. So obviously, at 0% is the content basically being encoded, typically with a normal encoder while trying to preserve the grain itself. At 100% is basically the equivalent of implementing FGS completely, and you basically have no grain in the contents, and the grain is entirely synthesized. You can see the bandwidth savings already just by looking at the difference between 0%, which would be no FGS at all, to 100%, which would be implementing FGS. Now, if you look at hybrid FGS with the grain preservation. So again, remember, we're using a scaling factor. So if we do grain scaling with 3/4 of the grain being preserved in the video itself and 1/4 of it being synthesized, we can actually already achieve some savings, and obviously the savings increase as we also increase the scale of the grain that we decide to synthesize itself. As a point of comparison, if you look at, for example, the dinner scene itself, if we synthesize half of the grain and preserve half of it, we're basically already achieving, I want to say 35% of bandwidth efficiency while still preserving some grain that could be used to address legacy devices. Visually, how does that look? Well, here's a crop on the dinner scene sequence. Again, the full preservation using a regular encode, no FGS at all with the 18 megs. If you do a 3/4 scaling, you're looking at 11 megs, so that's 39% bitrate gains already, and 2/3 you're at 50% gains. If you look at on your left, a device that has FGS enabled, you're basically just going to see the grain again. Now, if you're going to see, going to use a device that does not benefit from any FGS implementation, you will see gradually as you change the scaling factor, you may lose a little bit of the grain, obviously, because you're synthesizing more, but you can still address some form of the grain for those markets. So now, we've done the state of the art. We looked at different methods to address grain. We've looked specifically at how would grain attenuation look. Let's see what we can do from a dynamic standpoint. Well, if you think about what we've said so far, the FGS itself the benefits of FGS vary depending on the total number of devices, the programming itself, the content, type of contents, and finally the share of FGS capable devices. So looking at just introducing FGS in a very static way without looking at how dynamic those parameters are seems a suboptimal way to respect the artistic intent and make sure we can deploy FGS at scale. So our idea was to look into, is there a way we can implement this in a dynamic way, having this methodology to partially preserve grain whilst preserving the full grain for an FGS-capable device, but also having some form of awareness into the encoding. And that's where we, at the time, we actually were lucky enough to do some research on audience-aware streaming. So we have the ability to allocate resources based on analytics that we have within the encoding system, which allow us to then reallocate resources on specific profiles or add more or less and dynamically. So we can use the same dynamic capacity of the encoder in the context of FGS being transmitted to both FGS-enabled devices and legacy devices. In this way, we could then activate and deactivate grain preservation mode for HVC codecs or legacy any other codecs. We could add the presence of an additional codec profile for simulcast, for example, with reallocation of the CPU cores. We could also degrain. We could also add the degraining of scaling factor on HVC itself. So again, looking at the overall process and this whole story, we went through the entire process to see if we could implement this in a dynamic way. Now let's see, why would someone do this? Why would any media provider today look into the specific scenario? Well, that's the keyword, right? There's different scenarios based on what you're trying to achieve. Are you trying to provide the best preservation of grain? Are you trying to lower having the lowest total costs on your CDN side? Well, if you're looking at providing the best preservation of the grain itself, you can always provide the full grain preserved content with the legacy codec as part of this criteria. AV1 codec profile with from grain synthesis could be added to decrease the overall traffic. But that obviously depends on whenever the total amount of compatible devices is sufficient and corresponding. A different scenario would be to use film grain synthesis and degraining simultaneously to avoid hitting the hard limit of the CDN bandwidth. That's if you have a specific CDN infrastructure and you want to make sure that you can address the market, but still you don't want to hit the limits of it. Another use case is to look at the lowest delivery cost with preserving grains while preserving grains as much as possible. In that scenario, we would be removing all grain on legacy codecs and adding an AV1 FGS codec, the profile to decrease the overall traffic. The saved traffic costs ultimately outweigh the additional encoding costs. So again, you're doing simulcasts, regular legacy codec while you're encoding AV1 with FGS. But since you're actually saving on traffic, you're ultimately saving money. FGS here is a side benefit of AV1, and part of that's actually in the manuscript and the paper that we submitted. Part of these results show that you have a pretty much linear savings that depend both on the share of grain contents, the cost savings, but also those results will vary depending on the total amounts and the share of AV1 devices and AV1 adoption on the field. Finally, another use case was to actually tolerate a maximum number of viewers to lose some grain, but always seek the lowest delivery cost. In that scenario, we can use the degrain scaling factor depending on the population that is capable of using FGS, whether it's AV1 or AFGS1. In the case where the permitted share is FGS capable, complete removal of grain is possible. If conversely no device is FGS capable, then some grain was preserved in the legacy. So again, we end up with cost savings are increasing depending on share of grain contents, and this was specifically done for 5% degraining strength, if you remember what we mentioned earlier as part of our grain attenuation. So as a conclusion, I know there was a lot of text. I promise there's a method to this madness. But basically, we looked at this current state of the art with and trying to ensure, because we wanted to address some potential deployments of FGS. How would we actually go at doing this today? FGS deployment must consider the current legacy and the current legacy devices that exist today, and still make sure we can preserve the grain and some form of the artistic intent for those as well, and not instead of just enabling FGS for specific devices. If AV1 obviously is used, then you can immediately use FGS without restrictions. If you have other codecs, there's currently no way, and we're stuck in this one size fits all. The method that we discussed different methods between the partial degraining, grain preservation, and simulcasts. And finally, as part of this, we looked into dynamically triggering these parameters based on what is optimal, based on, again, number of devices, sub-contents, and number of total end AV1 devices, in a way that we created this incredible sentence for client audience capabilities and content-aware film grain synthesis and additional end-to-end delivery optimization. Copyright pending. That's a joke. Sorry. The next steps for us after looking into the study, and I want to make it clear here, is we're not trying to make a recommendation. This was a research study. We're looking at assessing the gap between what is effectively on the field today and what is separating us from implementing FGS in the future. And what we could do as part of future work is subjective testing of the proposed methods that we showed in the study, potentially looking into signaling on a production side that there is FGS that is content with grain to preserve, in the same way that we, after all, have some signalization for HDR contents that we need to preserve as well. And finally, as part of the dynamic aspects, we could develop orchestration model for grain optimization within the encoding, within different encoding systems. Thank you. And we had this on grain on the last slide.
I thought the projector broke. Thanks, Robin. Are there any questions? Ben?
Thanks. You were saying earlier about how you kind of assume FGS for any AV1 decoder. However, tragically, we tested a lot of early models and found the FGS rendering components are not quite normative and have various bugs early on. Have you found any paths in which to make the FGS work well on some of the older devices, at least detect them so they don't get sent FGS content?
I'm sorry, is the question, have we validated the actual FGS just working with AV1 on different devices?
I know there's a lot of devices that have shipped, especially the early rounds of it, which don't have conformant AVFG1 rendering modules and cause all kinds of weird artifacts. And so we found that we can't really, you can't reliably assume you can do FGS on any AV1 decoder. I was wondering if anyone looked at either ways to make more compatible FGS and metadata, or to figure out which devices can't do it well and not send it to them.
Now that's a good question. I know we've done some research on AV1 with FGS already. I think it's still very much in the progress of the optimization. If you're looking at, in the same way we're working on optimizing VVC today, I think FGS is going to be a rollout as part of this, and we're still working on optimizing that workflow. So the short answer is, I'd say it's a work in progress, and I don't have a better answer today.
Okay, thank you.
Yeah.
How do you reduce the film grain? Are you removing it entirely and then just adding it in at a low strength, or are you just somehow processing the image with the actual grain in it?
So, I mean, that's part of the film grain synthesis itself. So when we're receiving the content, we're capable of actually detecting the grain itself and removing it and synthesizing it. As to how we actually do it, I mean, I would assume it's part of some of the pre-processing that was not this. I don't know if it's pre-processing, but it's something we do internally. I think the method of which I would have said, no, I do not know. Yeah, I'd have to check internally. I'm not sure, Thomas, if you actually know how we specifically do it. I'm sorry? Yeah, it's within the preprocessor, basically.
Right. Well, obviously, it's part of the preprocessing. I was just curious if it was like you were somehow preprocessing the actual grain itself, the content with grain, or if you were removing it and then injecting it back with like a lower value.
Sorry. So we can use a threshold to determine how much we want to remove. So the part of the paper is about how we can decide, at least at an initial stage when there is a lot of devices out there that kind of can't use that film, we can leave it in the picture so it goes through the encoding pipeline, to your point, and just be conservative in the amount of grain we actually remove. We can discuss more if you want. And while I have the mic, maybe Ben. So yes, we did find some device out there at first that did not properly follow the spec and resynthesize the grain. What we found out in some cases that they were fixed. Some streamer out there put pressure on consumer electronics to fix their implementation. To your point, there are some that couldn't be fixed, and they are still out there. So far, what we've seen being done is basically whitelisting. So using device ID to know which one are problematic and make sure they are not part of the pool. And those can be delivered a non-degrain AV1. In fact, the work we've done on grain preservation is also applicable to AV1, and we do that. But some people might just, if available on the device, just send the traditional HEVC stream to those devices instead of the AV1. So it really comes down to an economic decision more than a technical decision. Hopefully over time those devices will get drawn out by the new devices that do support AV1. So we encourage all our customers to continue pushing consumer electronics to go through their test case scenarios. And we're happy to help. We did that with multiple major TV manufacturers and SoC vendors. Yeah. It's one reason we felt it was interesting to get a gradual approach where you can set a threshold and move it over time.
All right. With that, thank you, Robin. And I think we now have some tours for the exhibit hall. And while you're there, make sure you take a look at the IMAX booth. It's an actually really interesting demo to see the repetitive patterns and how they're really distracting and definitely need to be solved. Thanks for joining and enjoy the rest of the day.